All right, I guess we can start here. Let's see. All right, reminder, tomorrow night, I run Bug Submit. Not Bug Submit, I run the AutoGrader. And briefly, and you'll get anyone who has submitted something in the normal fashion will get results. I've neglected to put up a proper pre-testing, trivial pre-test for Project 2. I will try to remedy that before the evening, so that you can tell whether your submission is going to be, so you can tell ahead of time whether your submission is going to be rejected on some silly ground, like, for example, you forgot to submit a file, or you left out testing, or you fail your own pretests, or something like that. So even if you fail your own test, even if you fail the pretest, you can still submit, but you've just been forewarned of the problems that you're going to run into. So we're going to be doing another little coverage test. The coverage test this time is only of errors. So we look to see what error messages your tests produce from our compiler and see how many of them you get, how many of the conditions you get. Some of the conditions are ones that I'm not, since some of the things that our compiler reports are not things that are clearly errors, those messages won't count. And again, we'll be checking to make sure that the things we only look at tests that don't look like AutoGrader tests. I remind you, I do want your tests to be original. Please try to do your own testing. And finally, please make sure that your tests are in the canonical places, tests/correct/tests/incorrect. If not, we won't, otherwise we don't know where to look for your tests. So please put them in those places so we can find them, yes.
Does this mean, will we be given test files that have multiple errors?
No, we don't do it, no. So one of the things that I've done in my past, in my youth, relative youth, was I was involved with a group that did testing of Ada compilers. So we were the official people in charge of ruling on whether tests were in this validation suite were correct or not. And the way that these validation suites work is that each one of them tests one thing. As a result, the validation suites were huge. They're just, you've got a manual this thick, and so every page has several things that has many errors on it, and so you've got this huge number of tests. And in fact, they would take something like 24 hours to run these things. So that's the way it's done. You don't test multiple errors. Now, of course, if there are multiple errors in a file, you're not supposed to blow up. You are supposed to report at least, well, you know the rules. You report at least one of them, and then. But if we see exceptions, if we see your program exit for malign reasons, then that's not considered good. Hand over here. No. Yes. Maybe. No. Okay. All right. So we're going on. We were continuing our discussion of special effects, and the special effect of that we ended last time was exceptions, and the design of exceptions, the mechanism, and also its interaction with the language, with the implementation. Okay, well, so design one, don't do anything, and there are actually advocates of this design, and as you know, the C library took this approach. I should say there is another thing that I didn't mention, and that is when something goes wrong, stop. That's another thing. If something goes wrong, you stop. And there is a famous computer scientist actually advocated this. Recently, a famous computer scientist and Turing Award winner by the name of Tony Hoare, H-O-A-R-E, advocated that. Another famous computer scientist by the name of Barbara Liskov was visiting here a couple months ago, and so I shared with her my puzzlement at this and asked her, if she had any idea what he was talking about, and she said no, she didn't. And so she's with me. She's with me. She thinks he was crazy, but he's still famous. What can I say? You've heard of Quicksort? Okay, that Tony Hoare. All right, so this is non-standard return is another technique. This is an implementation technique, although you can also, it's not clear what this is something you can do in the language design. So this technique is at the assembly, we're talking now, we've just dropped down into the assembly language level. So when you return from a function, most architectures give you a way of returning to the next instruction after the call, but you can also return to arbitrary offsets from it in most architectures. So we'll just do this. We'll have something that normally you return and you jump to the OK, and then you jump either to the next, or you come either to the next return instruction after the call, or you jump over that instruction to the one after that. All right. Well, of course, if you do it this way, then so that means you could have a feature in this could translate into a feature in your programming language where you have a call and then you have something that says, or you can have some section of code and something at the end of that section which says what to do if any of these calls come back exceptionally. You could do something like that. Sort of like, which is like try, which is kind of like try in Java or C++. Okay, well, this is fine, and it works. So in the case of the IA32, of course, you have this problem that so in the IA32 you sort of have to cons up the return, as I recall. But in other machines you can do this easily enough. I don't know why I asked that question because it's kind of obvious. You have the address and you have the return address in the register, so you just do the return to the appropriate point. Now the problem here is that if you do it this particular way, you have this extra jump after every call, which may or may not be, that probably doesn't matter too much. Assuming that exceptions really are exceptional, branch prediction will do the right thing. Maybe, I don't know. Will the branch prediction do the right thing? Well, certainly the jump is okay, but it's the return that's going to be kind of problematic. So I don't know. I'd have to measure it. So there's some slight problem there. You could reverse the convention and jump over the next instruction if it's normal, and then you could just then it would be easy because the return would go immediately on with the program. Of course, you have to be careful that all of your languages comply to that, or because if you were calling C and C wasn't using that, and the C implementation wasn't using that convention, that would mean you'd have to have extra little dummy routines every time you call the C routine, or you'd have to call C routines differently. So there are some complications, but this can work. This can be done, and it's sort of the basis for a mechanism of just communicating an extra piece of information, sort of a side channel out of any function. You can communicate the exceptional condition on which that function returned. And you might use it, in other words, you might use it to implement a bunch of different language features. So here's another implementation. one is used in the C library in typical C implementations. And it works like this. It takes advantage of the fact that we typically have this call stack. It's a stack. And that the information that you need to return to a certain place, to a certain point in the program is the program counter, the PC, of that return point, and the location of the frame. So the stack frame top and the stack frame bottom. And maybe some other registers. That's where things get a little problematic. There might be some other registers you need to restore. So what you can do in C is this thing. How many of you, by the way, how many of you have seen this? Set jump, long jump, set jump, long jump. Okay, there are actually two of them. There's another one for jumping out of signal handlers, which for various reasons has to be a little different. It works like this. We have a code that looks like what you see up here. So you have an if statement. You call the set jump routine in this if statement. And normally, the first time you call it, it returns 0. So the effect is that you come down and you execute the normal code. And then eventually that normal code will say callee. And callee encounters a problem. So it does this other call, long jump, mentioning a certain data structure that I've called catch point. It's called a jump buff, which resembles Australian slang for kangaroo, I think. And when you do this, the effect is that all of a sudden you find yourself, basically the long jump stores this information in a data structure like this. This is what catch point looks like. And set jump does. And long jump basically takes the frame information out of here and restores it so that all of this stuff goes away, and you're now right back here executing, returning again from set jump. It's like one of those fantasy movies where, like Groundhog Day, I guess it was, where the guy keeps waking up on Groundhog Day over and over again. So that's sort of what happens here. We wake up after set jump again, returning from set jump, except this time set jump, instead of returning 0, returns 42. So this time we take the exception branch. Sounds kind of weird, okay? But if you have a language where you're not going to add a language feature, you're just going to do it in the library, then, that's the sort of thing you end up with. That's the sort of weird thing you end up with. So this is how it works. It just uses the implementation of C, or abuses the implementation of C to create this effect. And these are official members of the C library, so it's not as if it's doing something completely weird. Presumably the library writers and the C compiler writers are in cahoots, and they make sure these things remain coordinated, which they usually do. All right, now let's see. Do I say that this has a... Okay. So, and you notice that the amount of material, the amount of stuff that can be thrown away, callee's frame and other frames, is arbitrarily large. So it's not just one single return from a function. You return from a whole nest of functions back to a certain point. So this is pretty good. Unfortunately, it has a little bit of problem. I say it doesn't require help for the compiler. It sort of does. It requires that the compiler conform to the library's idea of how, or the library conform. The library and the compiler have a common notion of what the runtime structure looks like. And of course, it has this problem that every time you want to do a set jump is not a free operation here. It creates this, it stores all of this information in the data structure. And the amount of information depends on the architecture. There's also this weird little problem, which is that, and it's basically a problem that is indescribable as far as the language designer is concerned. So, and that is that typically, in order to work in general, the thing has to restore registers as well as everything else. I mean, you typically store some variables in registers. So what this will do is it restores all the normal registers that a function call would normally restore, like setjump. It restores all of those registers. And the problem with this is that if the compiler doesn't know that setjump is really weird, it will be under the impression that this is okay. It'll be under the impression it can possibly result in rolling back the values of some variables to what they were before the call. And this can, in some cases, in some obscure cases, cause problems because that's not what's supposed to happen. All of the values of variables are supposed to be exactly as they were at the point you did the long jump, at the point you returned, just as in Java. And the only thing that's supposed to change is where you are in the program. So there is this slight problem. I haven't actually ever encountered it. It requires a certain amount of aggression on the part of the compiler, and I think usually compilers manage to avoid it. Okay, so that's fine. But that brings us to approach 4. So the big downside of setjump, long jump, is expense. It's expensive to save this information each time you want to go in. So along comes PC tables. Now this is the approach that's used in Java implementations, and it's sort of built in, and there's a mechanism for it built into the Java runtime, into the Java virtual machine. In fact, if you examine class files, if you go and look in the book and examine the format of class files, you see that they contain a particular kind of table that is talked about here. So here the idea is very simple. We'll simply have the compiler. The compiler, if exceptions are part of the language, then the compiler knows every piece of code that's supposed to handle an exception, and it knows what exceptions are caught by a specific procedure within any piece of code. So it can create this table that says, it can create the table at compilation time. It gets the final values get set at runtime, at link time, that says that maps program counters, positions in the program, to exception handlers that are supposed to handle exceptions when you're in that part of the program. Right? So it can this is a fixed map. It's computed at compile time, and there's no cost to it at execution time. It's just there at except for the space that it takes up. So all we have to do now, we also need a way of unwinding the stack. That is to say, there has to be some general mechanism that allows you to pop off the latest stack frame and do a return from whatever function you're in, sort of generically. All right, so then this is what you do. If you get an exception, the effect of an exception is that you go to this little piece of code that looks to see whether at the moment your program counter, according to the current map, your program counter is, or what exception handler applies to your program counter. If no exception handler applies, so for example, you're in a function that doesn't have a try in it, then you return you pop that function off the stack. You pop the function, and then you now have the address that the caller to that function where the caller is, the return address to the caller, and you look to see what exception handler is supposed to handle that, and so forth. You keep going back until you find, according to your table, that you're at a program counter, that a position in the program that has an exception handler for whatever exception has just been raised. And then you say, okay, fine, we'll stop here. We will branch to that. We'll branch to where this table tells me, and we're done. So that's it. That's the PC table approach, and it has the considerable advantage that, as it says here, there's no cost at execution time until there's an exception. It's kind of neat. The problem, of course, is that it's no longer, it's a rather expensive business to throw an exception. So if you had the idea that you were going to use exceptions as sort of a, not an exceptional thing, but as a rather sort of run-of-the-mill everyday data structure, or a control structure, then you might have some problems. For example, Python uses exceptions to stop iterations, to stop loops. So when you say I'm sorry, I should say, well, yes, it is actually part of the language. So when you do something like, say, iterate through the elements of a list, you get to the end of that list. The way that Python works is it says at this point it throws some kind of exception, which one I forget, and that's what tells the loop to stop looping. Yes.
I just have a question about how Java works.
Yeah.
Does this mean that your main function is like automatically augmented with exception handlers for all different?
Nope. It's only one exception handler for each. It's only the only exception handlers are in those places where you have tries. Oh, I see. Well, there is something, if you unwind the stack all the way so that you pop off the main routine, then yes, there is something that notices the unwinder says, oh, look at this, we've come to the end of the list, that means this thread dies. So it kills the thread. So yes, but that's the unwind handler. The unwind handler just says, okay, obviously this guy is not prepared to handle this, fine, he dies. I will put him out of his misery. This is thus causing, of course, what this does is it causes a thread death exception someplace. So it's kind of strange. All right, so that's how this happens. So these are the sort of principal mechanisms. Let's see what we've got here. Yes. So these are sort of the principal mechanisms used these days for handling exceptions. Each one has its pros and cons. So you have the pro of absolute simplicity for the for the do nothing method, except perhaps for the programmer. You have the fact in the case of the C method, you have something that you can add without adding a new language feature, just doing something to the runtime. And this has a few drawbacks, not the least of which is that it looks kind of weird. Oh, by the way, I didn't say it, but this is, of course, what you've got here is something that allows me to return to a single catch point. What would you do if you wanted to reconstruct? We can reconstruct with this mechanism. We can reconstruct Java's mechanism. So there are two things missing from this mechanism. First of all, dynamically nested exception handlers, where you have several different places at which you can, at which an exception can, or several different places that can catch exceptions, and they're all simultaneously active. Right, so this doesn't have that. And it also does not provide a way of returning a value the way Java does. So in Java and in C++, you can return an arbitrary value as part of the exception. You can say the foobar exception occurred, and here's some extra information, huge volume of stuff that you can pass along. And this does not have either of those. So how would you provide them? It's an important question because C++ uses C, so obviously it has to have solved this problem somehow. How would you solve it? Again, I want to reconstruct Java mechanism using just this. Any suggestions? This is a small matter of programming, as they say. You have to do a little data structure hacking. I see one. I see the usual hands. May I see some more hands? Maybe I should just call on somebody at random? I don't know. All right. How about, what do you think?
In catch point data structure, you can add another value in that data structure?
Well, not exactly, because catch point is a jump buff is a library routine that's already written for me. But I mean, I'm the programmer. I'm writing this program, and I'd like to get Java stuff into it. I can use jump buff, but let's assume we can't change it. But I can use it.
I guess you could have like a table mapping each catch point to a different value. Look up in that table.
A different value of what?
Like, let's say you want to throw like a string
Uh-huh.
on catch point. So that there's a big table when, like a map, you get a catch point and then it maps you to that string that you just threw.
Okay. So you could. So that's a way of returning. That's one way of returning a value, sure. But that doesn't quite answer how it is that I could be returning to, at a given point I'll do a raise, and I don't know which buffer to return it, which of these catch point buffers I should be using, because I don't know which function at the moment is the innermost one, the most recently called one that I should return to. Yeah. Yeah, I'd have a stack of jump buffers, and every time I get an exception, I go to the top thing on the stack. I see if it's willing to handle this, and if it isn't, then I pop it and I jump buff and I long jump to the next one and so forth. I just go down the list. So that's, and I could, in fact, to return the value, I could just have a single global variable that contains the value. How's about if I returned a pointer to the value? How about that? Yeah, I could return 42. That's easy enough. How about a general value? How about I return a pointer to it? I'm looking at you with a predatory smile on my face, which might suggest that there could be a catch. Pardon me? Okay, well, there is this issue. You have to have agreed on what type of message you can pass back. But, okay, fine. We'll just, I can, that's easy enough. I'll just agree that it's always type exception info or something like that. I can do that. But there's a gotcha that I have to be careful about. Maybe you're not answering because you know, of course, I would never do that. So I can't understand why he thinks that there's a problem, but I am thinking of a problem that I have seen in your code. Yeah, back by the wall.
It's the value that you want to return.
Yes, exactly. So if you do something silly like build a local variable containing the value that you want to return, and you say, okay, return a pointer to this variable, well, you'll return exceptional garbage. So, yeah. All right. Important thing to remember. Yes, memory corruption problems of that sort are very common. In fact, of the last dozen bug submits that the TAs and I have handled, I think almost all of them have been somebody forgetting to ref something that he should have refed. So, which is interesting. I don't know. Have you responded to any bug submits that weren't that? Oh, I see. Okay. Yeah, oh yes, that's right. There's also there was that one. Yes, okay. For each, if you do a for each and you remove something or you replace it with more elements, then you will be repeating. You'll do a repeat on some elements. But yeah, I saw one of those too. But most of them have just been refs and releases. Which is nice because it means that I can really whip through those bug submits. That's kind of useful. I say, okay, and he says something weird is, okay, let's look at all the places where he does replacements and see if he's doing the refs properly. No, he isn't. Okay, tell him that. Yeah, it's great. Yeah. Makes me look like a genius, but all I'm doing is running grep. You know, it's really... It's great. Okay, fine. So this is exceptions. Basically the mechanisms behind them and how you use them. So it's time to go on to another topic, but first I think we'd better take a break. So if there are no further questions on this, let's just take a break.
Question about 61A.
Uh-huh.
Well, sorry, can I ask you a 61A question? So, you know how when you have a Lambda statement,
Which statement?
a Lambda statement,
Yeah.
it's supposed to encapsulate the environment in which that Lambda was created in.
Yeah.
Does Python do that?
Yes. Supposed to.
It's supposed to? Okay. Even if you have like a callback, it's supposed to store the values you're passing into the callback? Mm-hmm. Okay.
Now, it's an interesting question. I'm going to have to, I should probably check that because it's something you don't do very often in Python.
Right.
It's something you don't actually do very often in Lisp either, except in 61A where they're sort of making this point.
So in Python, if you have something like for m in messages, where messages is a list, and you say func_list.append lambda callback m. So you have a function list where you keep appending lambdas to, and in the lambda you make a call to the callback, and you're passing in the element of a list to the callback. It apparently doesn't save the environment in that case.
Now I'll have to look into that. So you do a for, so you create a list of lambdas.
Yeah. Just right on the board.
And you create a list of lambdas, and what variable is it that doesn't seem to get saved?
So if you're iterating over a list, so for m in messages, m doesn't get saved. It gets saved as a pointer. So if you have messages...
Yeah, but that's what happens in Scheme as well, right?
Really?
Yeah.
Oh. I thought m would get saved. So if you have like... Oh, okay.
Now in Java, you can sort of think of it as getting saved because in Java it's required to be constant. So it can't be changed afterwards.
Okay.
How they actually implement it, I don't know. Yeah.
Okay.
Yeah.
I thought that was like...
Yeah.
All right. Thank you.
All right, let's dive into this next topic here. Okay, so for a couple of years now, I guess you've been using this. You've been using Java and OOP. You see it in 60. You see all of the important mechanisms in CS61A as usual. So this mechanism and I'm referring specifically to instance methods here. Dynamic method selection, meaning the cases where you're selecting a method out of an object. This was introduced originally by in Simula 67. That was the most prominent one. They may have occurred elsewhere, but in Simula 67, no, it was not invented by Smalltalk. In the 60s by Alan Kay, no, or the 70s by Alan Kay, no, he was not the inventor. No, he was not the person who elucidated its advantages and so forth. There were other people who did that. I'm sorry for hammering on this, but these revisionists are always coming along, and so it's always hard when you've actually lived through a period, so you know what it was like because you were there, and then some idiot whippersnapper comes around and starts crediting the wrong people. You really get angry. Okay, so but there you go. All right, so this was technology introduced in the late 60s, early 70s. And the idea is we have this hierarchy of types of some kind, and we think of this hierarchy reflects the sharing of certain characteristics among all these various types. So that, for example, we can say that a car is a vehicle. That is, it shares with other vehicles certain properties, like the distance it's been driven or moved or something like this, the amount that it can carry, that kind of thing. And we take advantage of this in first being able to write methods that generalize to all vehicles, as opposed to having one method for cars and one method for bicycles and so forth. And the whole idea is that, and the thing that's different about it, that's unique, is that in general you cannot tell statically at a given point in the program what text, what body of code is going to handle any particular call, because it depends entirely on what specific subtype of the type that you're acting on you've been passed. So the question is, again, how we implement this thing depends on what the language, how the language presents it, how the language contains this particular feature. All right, so there are a few things that we usually keep static, that still remain static. So, for example, the names of functions and the numbers of arguments. Now, this is, I say, usually known because there are features you're familiar probably with. Well, I guess in Smalltalk in Ruby, you could have a case where the message that's, as it's called, is the particular method that comes in has an arbitrary name, one that's been made up, and there's some calculation that has to be done about how to handle that. But usually we have the case that you know what sort of arguments this thing expects in a language like Java. If you've overloaded a name, then you have figured out which of the overloadings we're talking about, and so forth. And this is, by the way, this is an explanation for those of you who have never seen it before. How C++ encodes handles overloading. It basically says, well, if you've got two functions and they have different types of arguments, so they're actually, morally, they're sort of two entirely different classes of functions, completely distinct from each other. Sometimes that's called ad hoc polymorphism. So what it does is it handles this for the benefit of a linker or C compiler that doesn't know about this stuff. It handles it by the technical term is mangling the name of the function so as to reflect the types of its arguments. So, for example, the function fint contained in a class Q looks like this, which is pretty awful. And that means that I am a member of class Q. Q has a single letter in it. That's what the 1 is here. My name has one letter in it. It's F, and my parameter is an integer parameter. It's that E. I don't remember what the E is. So anyway, and I am a function and so forth. So this is kind of cute, but it's not very important. So let's just concentrate on the instance method part, the dynamic dispatching part. All right, so we have the technique that's used in Python, which is basically fully dynamic. That is to say that each time, in principle, each time you try to do a method call, and by the way, I should have been careful. Regular Python as it is usually implemented, the usual sorts of implementations of Python. So when I call if I have an instance of class A and I call A.F, then what happens is that in both of those cases, I fetch the current X value and the current F value out of X. And, well, that's easy enough because, in this case, because at the moment, neither one of these things has attempted to assign to either F or X. So in fact, what happens is, well, let's go on and see what happens. Now, if at this point I set the X value of lowercase a, X value of the object A, to a function, a random function, and I set the F value of A to a random integer, and I add a new instance variable, W. By the way, these are all illegal in our program, in our dialect, so don't be misled. Now at this point, I can print A, X, A, and F, and it's just as I just said it. In other words, the lambda has been changed. The lambda, the A.x is now a function, A.f is now a variable, A.f, and A.w is now a variable. So that's fine. B is the same as it was before, which means in particular that B.w does not exist, so it doesn't get printed. Furthermore, if I ask for the X value of A, I get 2, the same as before. So what's happened here is that I have, well, so far what it looks like is that when I created an A and when I created a B, I made a copy of what was in A, and I can modify it independently for both A and B. Now, however, I can also change the X value of A, capital A, to something new, and the F value, and I can add a new field V. And at this point, when I print out CX, CF, and CV, I get 19, 2, and 1. What I should have had was another line here that prints out these values for B, B.x, B.f, and B.v. What happens in regular Python when you do that? Does anyone know? Suppose that I did the same line here, but I changed all the C dots to B dots in this program. Yes, B, little lowercase b. What would happen? No. Who knows? Yes. Huh. Hope you didn't throw away a chance to get brownie points by. Now, anyone know? Anyone know? I believe you'll find that you get the same values as for C. The reason is that when I say that Python is dynamic, I mean it's really dynamic. the actual algorithm is that if you ask for the b.x field in the instance B, well, B, you'll notice none of those fields have been changed. So in fact, they aren't actually in the instance B. Instead, it'll say, oh, I haven't made any definition of X or F or V, so I'll look to see whether my class definition has it. Oh, look, here it is. And it will return those new values. Of course, the moment I set anything in B, I will have created sort of a local instance, a local copy in B, which will then be independent of the class. So it's pretty weird. It's pretty weird. I'm going to add that line to this because that's a rather strange thing. And it's not, again, not in our project. Okay? Not in our project, but in regular Python. All right, fine. I'll see you whenever, Wednesday.